Right, so we learned about Bohr's model and how electrons absorb energy to go to a higher level and release energy to come down to a lower level. Next thing we want to talk about is the hydrogen atom. Why the hydrogen atom? First of all, Bohr only gave us the hydrogen atom because it is the simplest atom. It has only one electron. So it is very easy for us, or for him, it was easy for him to only explain an element with it's only one electron. There is no electron-electron repulsion. It's not that when you heat it, there are too many electrons in different levels and they're all jumping up to a higher level, all jumping back down together. So it would have been complicated if it was more than one electrons. So hydrogen atom was used to explain the spectrum. But what you see here is called the line spectrum that I will explain later on in a few minutes. But here what I was explaining you earlier on, this is the nucleus. When electrons go from a higher energy level to the lower energy levels, when there is a possibility that all the electrons, from 7, 6, 5, 4, 3, 2, they are jumping back down to the lowest energy level 1. Okay? So they are covering all this path. So they have the highest energy difference. Because let's say if this is 1 and this is 7, 7 minus 1 is 6, right? Compared to if all of these are jumping to 2 only, there is a less energy difference. And if they are jumping to 3, then there is even less energy difference. So my point here is that it depends what the energy gap is, or energy level gap is where they are jumping from. Based on that, there are different series. So the one that has the highest energy are the ultraviolet series. So whenever electrons jump to energy level 1, n equals to 1, there will be the ultraviolet or high energy level. When all the electrons jump from anywhere to 2, second energy level, that will be the visible series. And I will explain all of this in detail in a few minutes. And when electrons jump from anywhere out here down to third energy level, that is called infrared series. So what is the difference between this spectrum that you see and the spectrum that you saw right here? What I see is that it has very discrete lines, defined lines, whereas this one is all merged into each other, right? So when all the colors are merged into each other, I cannot really tell where the violet ends and the indigo begins and the blue starts. When all the colors are merged together, it is called a continuous spectrum. I don't understand why it is. So it's called continuous spectrum. I guess the visible light that we see, whether it is the sunlight or it is the light from the bulb, the white light, whenever we see, it gives us the continuous spectrum, means the other color starts where the first one ends. It continues all the way from one end to the other. Whereas elements have defined energy levels. So if this is the nucleus, then elements have defined energy levels. So it is calculated if the electron will jump from here to here, or it will jump from here to here, so we can calculate it. That's why for each element, when we make it go through the prism, we put the element, we attach it to the light, we make it go to the slit in the prism. We see these defined lines, okay, and that is called line spectrum. Higher the energy is, less the wavelength is. Okay, so because energy and wavelength is different. So what you see here, the nanometer, the 434 nanometer, these are different defined nanometers. Nanometer is the wavelength, which I will explain again in a few minutes. You will see that with hydrogen, I will only get these 4 defined lines. And it depends where the electron is coming from. If it is less energy, then higher the wavelength is, then I will get this yellow color, or anywhere in between. Let me explain it right here. When energy comes out in the form of waves, we get this wavelength. Only this part is what the visible light is. Alright, this is the only part we can see, because that's the part that our eyes reflect. We don't see anything else because our frequency doesn't match there. We don't see radio waves or ultra waves or X-rays because our eyes frequency doesn't match it. What our eyes work with is only this part. So we only see the continuous spectrum. But we have all these waves. As you see that if you increase the energy, you decrease the wavelength. Okay? So if wavelength is increasing this way, the energy is decreasing that way. But before I explain all that, you know what a wave is, right? It has the same crest and the troughs. And the distance between the two crests or two troughs is called lambda. Lambda is the wavelength. This is how you call it, lambda or wavelength. And I've been telling you that as the wavelength increases, energy decreases. So what I'm explaining to you is that energy is inversely proportional to lambda or the wavelength. Because if the energy increases, the wavelength decreases. It's like seesaw relationship. What does that mean? If I have this wave, right, versus I have this wave, which one has shorter wavelength? Of course, Do you know the frequency? What is the definition of frequency? The number of waves pass through a point in 1 second, right? That's the frequency. So the more waves pass through 1 second, more the energy is going to be. Are you getting the point? So, and which wave will have more frequency? The one that has a shorter wave. In per second, or however you write it, in per second, I will pass less waves of this nature than this nature. Make sense? Common sense? So that means the shorter the wavelength is, more the energy is, because I can pass more of it in this given amount of time. So my point here is that they're inversely related. And what do we do when we have to remove this proportionality sign? We add a constant in it. Okay? And so we're going to do E equals, C over lambda. That is the speed of light. Or it is also related to frequency. C equals to nu lambda is another equation. So I want you to know this equation, C equals to nu lambda. This tells you how the speed of light, which is 3.0 what? 3.0 times 10 to the 8 meter per second. Okay, that is constant. This sign that I'm doing a kind of cursive V, it is like a cursive V. Or in your book, you will see just F. It means frequency. But this cursive V is called nu. So nu is frequency. And the unit for the nu is hertz or per second. However you like per second. You can write per second 1 over S, or you can write per second like this, or it is hertz. But in IV, we use per second. Okay, so we're not going to use hertz, but hertz is the unit for frequency. So do you understand every single thing in this equation? C is the speed of light, nu is frequency, and lambda is wavelength. Why are we learning this? Because we are saying that when electrons jump from higher energy level to a lower energy level, the energy comes out, and that energy comes out in the form of a color. We have defined colors for each level, energy level difference, and it comes out in the form of waves. So since it is coming out in the form of waves, I would like to know how to calculate that energy. Okay, so that energy depends on wavelength and frequency. So to calculate the energy, I'm going to use the equation E equals h nu, or in your book, I'm just too used to writing this nu. E equals h frequency, however, where f is the frequency. So if I am given a frequency of a certain wave, I can calculate the energy. Now what is that h there? H is called Planck's constant. And why did I need this constant? Because as I explained you right here, that energy is directly proportional to frequency. More the frequency is, more the energy is, right? So to remove the proportionality constant, I had to put proportionality sign, I had to put the constant in. So Planck was the scientist who gave us this equation. So he said that if energy is coming out, it could come out in the form of particles or photons, or it could come out in the form of waves. But anyway, if we're talking about particles, we can calculate it like this. What if I'm not given a frequency, I'm given a wavelength? How could I change the formula? Can I say this? E equals h c over lambda? Does this make sense to you? Do you think that nu equals c over lambda or c over wavelength? Yes? From this equation, I can calculate the frequency, right? C over lambda, and I could replace it right here with the wavelength. Instead of having frequency, I could use wavelength. So it's easier to calculate the energy, no matter what, you're given frequency or you're given wavelength. Because you have two constants. C is constant, you always have the value of C, and the value of H is also constant. It is 6.638 times 10 to the power negative 34 joules per second. So this is the value of H, which is Planck's constant. So long story short, we learned two equations. We learned one equation, nu equals c over lambda, or you can say c equals nu lambda. However, this is the mother equation, so you can say that. And then we have E equals h f, or frequency. Do we understand these two? Based on this, you will be doing the worksheet that I had passed around. Now, I gave you all the values. I told you the unit for the frequency is hertz or meter per second. Not meter, just per second. And the lambda to be measured in meters or nanometers. The relationship between meters or nanometers is that 1 meter equals to 10 to the power 9 nanometers. So doing 8. 6.638 multiplied by 10 to the negative 34 joules per second. So if we understand the concept of energy and the frequency and the wavelength, I would like to go back to this page, and I want you to see how things are on this spectrum. So on this spectrum, we have gamma rays, X-rays, UV rays, IR, radio. So where do you think has more energy? Which one has more energy, which one has less energy? This way we have more energy, right? So more the energy is, less the wavelength is. Do you understand this? It's a very small wavelength. So small wavelength is more energy and higher the frequency, same thing. As we move to the right, after ultraviolet, we see the visible light. So this is where our eyes are. We see the color blue, yellow, green, because our eyes are reflecting that particular wavelength. We absorb everything else and we reflect that particular one, and that's the color we see. So our eyes can manage this spectrum, and then infrared has even less energy than the visible spectrum, and then radio waves has even less energy than that. Do we understand it? So that's why when it's radio waves, we don't really need to worry about absorbing those waves and being affected by it. Whereas if it is X-rays, you will be put a metal on if that part of the body is not going to be X-ray, right? Because this would damage our body because it has too much energy. It is able to penetrate deep into our body. Are you getting a point? So we must understand the concept. So higher the wavelength, less the energy, less the wavelength, higher the energy. So we need to understand these things. Then we need to understand the series. So now we are going to apply this concept that we learned before. Hold on. If you want an electron to have a transition from the less energetic infrared region, so if you wanted to go to the less energetic, which is infrared, would it jump to level 1 or level 3? 3, because that will be less energy. So we get that part. So these kind of persons will be on the test for a quiz. If you want an electron to have a transition in the more energetic UV region, then it needs to go all the way down, right? So the bigger the gap is, the more the energy is. And then you see that they have names to it. You have Lehman series, Balmer series, or Paschen series. It is based on the name of the scientist who discovered those. So you have to know the names in general, but not really memorize it. But you need to understand the concept of it, okay, for SL2. Any questions so far? So this is what I explained to you earlier, that we have peaks, the crests, and the troughs. We have wavelength, C equals lambda nu, F is frequency, and 1 meter equals 10 to the 9 nanometer, and all that. What do we use it for? The infrared information, when an element gives out the IR radiations, it tells us what kind of bonds it has, because it makes the atoms vibrate. So it tells us what type of bonds it has, and UV tells us what kind of transition it's going through. But you don't need to explain that into, you don't need to understand any further or beyond that. You see that there are different colors. Radium gives us this blue color, or this, reddish or orangish color, and the yellow color. These colors are very distinct to each element. We can identify the element by color. It's just like a fingerprint. Because for each element, electrons are going to transition from a particular energy level to a particular energy level. So it will only give out certain color of light. Okay? And we can identify it. But like I can give you an unknown element, just a white powder, and you can put it on the flame and can tell me, okay, this is the element, just because of the color. So it's just like the fingerprinting of the element. So there has been two theories so far I explained. One, that energy is related to wave nature of the, when an electron jumps down from a higher energy level to a lower energy level, the light comes out, and that light comes out in the form of waves, and we learned about that. And then there was another theory that the light comes out in the form of particles. So de Broglie was the scientist. He said that light has a dual nature. It comes out in the form of particles and waves. So this is what de Broglie is known for. So normal wave looks like this, a wave packet. So that light particle that I'm talking about is called photon. Particle of light is called photon. You can spell it like that. Particles travel in waves. So he's saying it is basically, it has a dual nature, and it is the particles who are traveling in waves. And waves can only happen in discrete chunks, so it can go this way and it can go this way. So you don't have to draw the models of that. You just need to understand that de Broglie gave us the dual nature of light. Okay, we had the wave nature of light, and then Planck was the scientist who gave us the particle nature of light, and then de Broglie gave us the dual nature of light. But this was Planck. He gave us the particle nature, the photons. So Planck was the one who said that energy comes out in the form of photons. That is why this is called Planck's constant. Okay. So if we understand this, can we solve this question? So I have a violet photon, so the violet light is coming out with that frequency. What is the wavelength in nanometers? And what is the energy of the photon? So what information do I have here? I have frequency 7.10 times 10 to the 14 hertz or per second. And I need to calculate the wavelength. Do I know any relationship between wavelength and frequency? Do I know any relationship between wavelength and frequency? What is it? C equals frequency lambda or nu lambda. You know, I was saying nu lambda. You know, nu is the frequency. It's the same thing. And in your book, I was seeing that it says F for frequency. So it is easier for you. So we plug the numbers in. Do we know the value of C? C equals to 3.0 times 10 to the 8 meter per second. And then what? To calculate the, yes, go ahead. This is the equation. Is this the right equation for wavelength?
Yeah.
So we plug the numbers in. Okay, so the seconds get cancelled. The only unit left is meters. So we do the math. Can somebody do the math? (1.2 times -6, -7 meters. -7. Do we get this? Okay, so this is the first part. What is the wavelength? But it says in nanometers. And we got it in meters. So how do we convert it into nanometers?
Times 10 to the 9.
1 meter is 10 to the 9 nanometer, right? Meters get cancelled. So we are using dimensional analysis to calculate or to convert the meters into nanometers. So what would it be then? 4.2 times 10 to the 2. Yes? So what would it be? 420. Is this right? Where are you getting 22.535?
That's the rest of the number.
Right, but I only need up to the, you know, it's only significant digits that I'm taking, but I just multiply it times 10 to the 9, so I'm only doing exponents. I don't need to do anything else. So that is my wavelength in nanometers. What is B? Okay, what was part B? What is the energy of the photon? How do we calculate the energy? That is an easy equation, right?
Planck's constant.
constant times frequency, right? Planck's constant times frequency. So E equals, what is Planck's constant? 6.638 or 6.626. There are different books are giving you different values. Time negative 34 joules per second. And you multiply it by what? What was the energy frequency? 7.10 times 10 to the 14. So per second gets cancelled. We do the math. The answer should be in two significant digits.
4.7 times 10 to the negative
4.7 times 10 to the negative 19. Did we get it? So what we learned overall is, in general, that the electrons jump from high energy levels or excited states down to the ground state. And whenever they come down to a lower energy level, they give up light. And that light comes out either in the form of waves or particles, right? But then de Broglie said it's a dual nature. It is actually the particles that are acting like a wave. Okay? So we can use either of the ways and calculate that energy that comes out for every single jump. So that's about it. The next thing we have quantum mechanical model, which we don't need to know. The only thing we wanted to know today was the emission spectrum and Bohr's model.